Hi, with all this knowledge about the gamma distribution, I will tell you a few things about the Poisson process, which can be derived by what we have already on gamma. I believe most of you have heard about the Poisson process. It is a process of random events in time, positive time. So these are the random events represented by marks, and there is a parameter, a positive parameter lambda. It's a positive real. Okay, and so there are several ways to define the Poisson process. One of the definitions is the following, that starting from 0, the first mark comes at an exponential lambda time, and then the difference, the waiting time from the first to the second mark is again exponential lambda and again exponential lambda. So it's always independent exponential lambda waiting times before the next mark. So these things are all IID. I'm actually going to call them xi's. So xi, x1 is the waiting time for the first mark, x2 is the waiting time between the first and the second mark, x3 is the waiting time between second and third mark, and so on and so on. Okay, this is actually an example of something people in more generality call a renewal process. In renewal processes, this exponential could be something more general, but for the Poisson process, we definitely need exponential lambdas, at least for the homogeneous Poisson process. Anyway, here is a little claim I want to show you. Why is this called a Poisson process? Here's a little claim I want to show you. Define n as the number of events, or the number of these marks, in the interval 0t. So here is some time t. In this picture, n of t turns out to be 1, 2, 3, 4. It's a random number, and so let n be the random number of random marks in the interval 0 or t. Then the claim is that this will have a Poisson random distribution of parameter lambda times t. Okay, that's the claim. And let's see how this follows from what we know about the gamma distributions. Before I prove that, let me just make a little notice here. This property is actually much more general than what you see here. It turns out that in any fixed interval we have Poisson number of marks. It also turns out that disjoint interval will see independent number of marks. Probably you've heard this before. And each of these is distributed here as a Poisson random variable with parameter lambda times the length of the interval we're looking at. But I'm just going to prove this much today in this unit, because that's a very nice application of the gamma distribution. And so let's do this. So I want to find out the probability that nt is k. Okay? And the way I want to find it out is, it's very difficult to handle these events n equals to k, but I'm going to handle them by bounds. I'm going to say that n is k if and only if n is larger than or equal to k, but not larger than or equal to k plus 1. So this event here, so here's my abstract probability space omega, and there is a big event here, namely nt is larger than k. Okay, and let's use another color for nt larger than k plus 1, which is clearly inside here. So that's the event nt larger than k plus 1. Why is that event inside? Because if nt is larger than k plus 1, that implies that nt is also larger than k, and so this event must be completely inside the other one. And now if I make the difference in the probabilities, then I exactly get this event here, which is the event that nt equals to k. Okay? And that's exactly the probability of the larger one minus the probability of the smaller one. So that's what I have written up here. This is my first event, and this is my second event, and the difference between these events, since one is completely swallowed by the other, is just the difference of probabilities. Okay, so now how can I handle these things? How can I handle these things with gamma distributions? Let's think about the event as we see here, that nt is at least 4. What does it mean for nt to be at least 4? Here's my first mark, second mark, third mark, and fourth mark. Nt is at least 4 exactly because the fourth mark came before t. Nt is at least 4 exactly because the fourth mark came before t. It's also at least 3 because the third mark also came before t. But if my next mark, the fifth one, happens to be here, then in this picture nt is not larger or equal to 5 because the fifth mark did not come before t. So what I want to claim here is that nt at least k is exactly the same event, that the fourth mark, or actually in general the case mark came before t. And this event there is exactly the same event as the k plus first mark came before t. Okay? So I have at least k marks from 0 to t if and only if the case mark came before t. That's the key. Now, where is the case mark? The case mark is at the position of the sum of k iid exponentials. These are the xi's. So this is the same as the probability that if I sum from 1 through k the xi's, then this is less than t. Okay? Whether it's less than or equal doesn't matter because it's a continuous random variable anyway, so it has zero probability event of being equal to t, so I don't really care about less or less than or equal. And then here, the same for k plus 1, right? The k plus first mark came before t means that the sum of the first k plus 1 exponentials is less than t. And I know exactly what the distribution of these things is. This one is the sum of k iid exponential lambdas. This one has a distribution of gamma, k, and lambda by the convolution property of exponentials and gammas. And this one has distribution gamma, k plus 1 and lambda. Okay? I know exactly this from the previous videos, from the convolution properties which we did. So all I need to do is look at the distribution function of gamma k lambda and the distribution function of gamma k plus 1 lambda to find out the probability of the event n equals k. So let's do that. Okay, so what is the distribution function? I'm going to write the distribution function as the integral of the density. So I need to look at the gamma k lambda density, and that is giving me a lambda to the k over s to the k minus 1, I'm going to integrate in s, and e to the minus lambda s over k minus 1 factorial. So what I'm integrating out here is exactly the gamma k lambda density at s. Okay? And I have to do the same for gamma k plus 1. So I'm going to write the integral from 0 to t of lambda to the k plus 1, s to the k plus 1 minus 1, e to the minus lambda s over k factorial ds. And I want to find out what is the difference between these two integrals. And this seems a little bit complicated unless, or as long as you don't realize that I can make a change in the power of k into k minus 1 by integrating by parts. So it's essentially just the product of a power and the exponential function. And those are very well handled by integrating by parts. So I'm going to say that e to the minus lambda s is the derivative of some function. What is that function? It's 1 over lambda and the minus sign e to the minus lambda s. If I differentiate minus 1 over lambda e to the minus lambda s, I exactly get back this function here. So I'm going to perform an integration by parts with this observation here. So I'm going to do an integration by parts using this observation. Okay, so let's proceed with this calculation here. I'm not going to touch the first one. So what is the aim? The aim is to bring this prime over to the s and make it k minus first power, so that I can hopefully compare with the other integral. So I leave the first integral as it is. Then Then I'm going to swap over the prime, but before that I need to look at the boundary terms. I need to carefully look at the boundary terms. What are the boundary terms? It's all the terms I had in front, and then it's the derivative or the antiderivative of what I had on the rear. So this is a product taken at 0 and at t. Alright, and then I have a minus, but there was another minus, so that gives me a plus. Integrate from 0 to t, lambda to the k plus 1. And then I have the derivative moved over from here to the s. So that gives me k times s to the k minus 1. And just the just what's left here is minus 1 over lambda e to the minus lambda s as a factor. I have to divide this by k factorial, and I have ds. Okay, so let's see what I can do with that. Now let's look at carefully what we got. We got a lambda to the k plus 1 over lambda, that's lambda to the k, and then here as well I have lambda to the k. So lambda to the k is the same. I have s to the k minus 1, that's the same. I have e to the minus lambda s, that's the same. I have an over k factorial after I cancel, that's the same. Here I have a minus sign which I don't have there. So actually these two integrals completely cancel each other out, and that's a really nice feature here because I got rid of all my integration at this point. Okay, so the other thing is I need to look at this term, this boundary term. The two minus signs cancel out, and I'm going to plug this thing at t first. I'm also going to cancel out with one of the lambdas. There is a lambda cancelling here, and so that leaves me with lambda to the k, then s to the k at t, so that's t to the k, then the lambda is gone, the minus is gone, e to the minus lambda t over k factorial. And when I do the minus, and k is at least 1, so I'm doing this, I didn't tell you that, but I'm doing this for at least 1. So for the moment, let's restrict ourselves to looking at the distribution of the mass function of n at least 1. And then, when k is at least 1, then s to the k at 0 kills out the other boundary term. So I end up with this quantity here, which is actually a Poisson mass function value at k, where the parameter of Poisson is lambda t. What is the Poisson mass function? Is the parameter to the k, which is here, e to the minus parameter, which is there, over k factorial. And so we concluded that at least when k is at least 1, then the distribution of n is the same as the mass function of n is that of the Poisson. So we concluded that n of t is Poisson distributed of parameter lambda t. At least we see that for mass function values at least 1. Now what is the deal with mass function value at 0? Well, if the two mass functions agree for every k except 1 point, then because the mass functions sum up to 1, it follows that this thing is also true. This also follows for k equals to 0. simply because the mass functions sum up to 1. So we concluded fully that n is Poisson of lambda t, and that's what we wanted to see, right? That's what we stated, that the number of marks is Poisson of parameter lambda t. In particular, if you want to find out the probability that n of t equals to 0, what is the probability that I have no marks whatsoever here, that will give me Poisson at 0, so lambda to the t to the 0 over 0 factorial e to the minus lambda t. This is 1, so it's just e to the minus lambda t. Of course it is, because that's exactly the event that I have 0 marks here from 0 to t, which means exactly that the first mark has to come after t, which means that the waiting time for the first mark has to be larger than t, and x1 is exponential of parameter lambda, the probability is larger than t is exactly this formula here. So everything fits together, and we just proved that we have Poisson number of marks from 0 to t in the Poisson process. Again, the Poisson process is a beautiful object. It much more than this is true. This is true for any interval, and disjoint intervals are independent, which is not seen from this proof, but at least this first easy step saying that we have Poisson number of marks follows from the properties of the gamma density.